All right, good morning, everyone, and thank you, Dr. Hewavitharana, for the introduction. Thank you all for being here, both in person and on Zoom. As Shashika mentioned, my name is Jack, and I've been a master's student here at Cal Poly, and I've been conducting research over the past 2 years regarding Verticillium Wilt management. And today I'm excited to share with you all the work that I've been doing over the past 2 years, and I hope you find it interesting. To get started, I'd like to thank my committee, the chair, Dr. Hewavitharana, as well as Dr. Gerald Holmes, Dr. Shenping Ding, and Dr. Lauren Gardner. I appreciate you and your support over the past 2 years, and thank you for being here. So to get started, today I'm going to be discussing a couple of different things. I had 2 different projects that I've been working on over the past 2 years. So today I'll be giving an introduction into the strawberry itself, the industry within the state of California, and then I'll be going into my research, with part 1 being evaluating the integration of crop termination, bed fumigation, and host resistance. And then I'll go ahead and turn to part 2, which is evaluating host resistance in 74 strawberry cultivars and elite breeding lines. I'll then give a brief conclusion about the importance of an integrative approach to disease management. So to get started, we'll start with an introduction to the strawberry. And I'm sure many of you know, within the state of California, strawberries are a big player in the state's commodity, and there's a large amount of acreage that are planted within the state. In fact, the state of California grows roughly 90% of the nation's strawberries, and we have 90% of the United States acreage located here. The industry itself is worth about $3 billion, and within that industry, 38,000 planted acres are usually planted annually. And that does change over the years, but the most recent numbers from the Strawberry Commission show that roughly 38,000 acres have been planted over the past 2 years. Within those acres, about 68,000 pounds of fruit is produced per acre. So that's a lot of berries. And I'm sure you guys love strawberries, or I hope you do, and you find that interesting. Furthermore, the growing region along California's central coast extends almost 500 miles, up here from the northern parts in Santa Cruz County and all the way down to the southern parts in Ventura County. And within this 500-mile radius, what we see is that there are 2 main growing districts. The northern growing districts in Watsonville, Salinas, which is my hometown. Main production occurs between March and November. And my mom and I like to refer to Salinas as the berry basket rather than the salad bowl of the world now, just because of the large amount of berries that are grown there. And then down here in Ventura County and in Santa Barbara County, we see here the Santa Maria and Oxnard growing districts. They produce the fruit roughly between January and May. And the thing about this southern growing district is they can produce a second crop as well. So within the month of June, they can go ahead and transplant more strawberries into the ground to produce more fruit and within the fall and early winter months. So although we see that the strawberry is a huge commodity within the state, there are obvious threats towards the production. And today I'm going to be specifically focusing on soil-borne pathogens. And there are a couple different pathogens that are main players within the industry. One being Macrophyllina phaseolina, which is the causal agent of crown rot. Another being Fusarium oxysporum, Forma specialis fragarii, which causes Fusarium wilt. Phytophthora captorum, which is an oomycete rather than a fungal pathogen, and that produces root rot and crown rot. And then finally, Verticillium dallii, which is what I've been focusing on and what I've been studying over the past 2 years. And just by looking at these pictures on our screen, we can see that above ground symptoms of these diseases look relatively similar. And just by looking at them, it would be hard for us to diagnose the causal agent just from the look of our eye. So specifically Verticillium wilt is caused by the fungal pathogen Verticillium dallii. And here at Cal Poly, we run a diagnostic service for the California strawberry growers. And between the years 2020 and 2021, roughly 20% of the samples that have been submitted to our lab have tested positive for Verticillium. And on the right side of our screen here, we can see those classic above ground symptoms that we just saw. But one noticeable characteristic about Verticillium is sometimes we get the presence of these black necrotic margins along the petiole of the strawberry plant, which can be a good indicator of the causal agent. And when we plate these infected petioles on a semi-selective media NP10, what we see is the formation of these black structures. And these black structures are known as microsclerotia. And these structures are really tough melanized structures that are the overwintering or survival structures for this pathogen. And these structures can survive in the soil without a host for up to 14 years. So we can see how hard this could be to control. and how the momentum can be built over time within many different cropping systems, not just strawberries. And when I mention many different cropping systems, that's because Verticillium dallii has a really wide host range. On our screen here, we can see from lettuce to strawberry to cotton, Verticillium dallii can infect many different hosts. And when we think about how sensitive these crops are to this pathogen, we can think of it in a threshold in terms of CFUs per gram of soil. And a CFU is known as a colony forming unit. And from our screen here, we can see that there's wide ranges of thresholds, but for strawberry, we see how sensitive it can be to verticillium. Levels as low as 2 CFUs per gram are enough to cause disease and crop loss. We see in other crops like lettuce, it's much higher, and in crops like cotton, it's much lower. So we can see here the wide host range of verticillium and the degrees of sensitivity to this pathogen as well. So when we think about the wide host range of verticillium, what we see here is that along California's central coast, we have a really habitable environment for growing a lot of different crops, strawberries included. But this temperate growing region is also a suitable environment for the development of these pathogens. And what growers often do along the central coast is they implement crop rotation practices. And the main reason they do this, and within the strawberry and lettuce rotation, we see that they can conserve costs using residual fumigation effects. So by fumigating the soil before a strawberry planting, they can reserve costs and use that residual fumigation for their next crop, which may be lettuce, for instance. Research has shown that no crop rotation treatments are better than the fumigated controls. And so what we see on our screen here are the two pictures of the same cropping system. And this is located just west of Salinas. And what we see here on the left side is a cauliflower and strawberry planting. And then on the right side, we see a lettuce and strawberry planting. We see here the cauliflower and strawberries were planted in March of 2020, whereas on the right side, we see that the lettuce now moved in July of 2022. So what we see here is that the strawberries have an extremely long growing period compared to other crops, but we also see the proximity of other hosts for verticillium like cauliflower, like lettuce. So we can see here how verticillium can not only manifest itself within these crops, but in strawberries as well. So when we think about how we could possibly manage verticillium and how we could prevent future disease and crop loss, there are a couple different methods that growers can implement. But first, we have to start with the phase out of methyl bromide. Methyl bromide was a really effective fumigant that was phased out under the Montreal Protocol. And this was mainly due to the depletion of the ozone layer, but also due to public perception of the harm it may cause. What we see here is that a 14% reduction in gross revenue was recorded with the phase out of methyl bromide. So how exactly do we fill the gap that methyl bromide left for us? There's a couple different management methods that we can implement, and some of them I'll be discussing today. One of them is crop termination, and we see here on the top picture of our screen what that could look like. Another is bed or broadcast fumigation, which is seen here on the bottom of our screen. And then another is host resistance, which we see here on the right side of our screen as well. So these are a couple different management practices that I'll be discussing today. And we can see here that possible integration of these management practices could give us the best outcomes moving forward. So cultivar resistance I just mentioned, crop rotation I just mentioned, as well as fumigation and crop termination. We can see how crop rotation could possibly not be a cure-all for the prevention of verticillium. But when we think about possible disease management techniques, we can look at the life cycle or the disease life cycle of verticillium. So on our screen here, we see a generalized life cycle of verticillium, and we can find in this life cycle possible targets that we could aim for. And when we aim for these targets within the disease life cycle, we could possibly cut off this disease life cycle and prevent the pathogen from producing overwintering structures, those microsclerotia, and prevent momentum moving forward. So specifically, when we look at fumigation, we see that fumigation can possibly target the microsclerotia that are in the soil. Now, on the other hand, we can see here for crop termination, that could possibly target the microsclerotia that are being actively produced in the crown and root tissue of the strawberry plants. So we can see here that these two different fumigation methods could target different areas in the life cycle, which could help us cut this life cycle off and stop the buildup of inoculum over time. So crop termination and bed fumigation, as I mentioned, are two different fumigation practices. Crop rotations are relatively new practice that's being investigated, and applications for crop termination are rather limited. But some of you may know what crop termination is, but others may not, and it's exactly how it sounds. It's going in and killing the crop after the last harvest to prevent the pathogen from producing microsclerotia. So on the right side of our screen here, we can see how that could possibly be done. What happens is that we can inject a fumigant through our existing drip system in hopes that these plants would uptake the fumigant and in itself stop the production of these black microsclerotia structures. We can see how that's different from bed fumigation. With bed fumigation, we don't have any plants in the ground. Our beds are completely covered, and we're mainly focusing on the prevention or the eradication of these structures from the soil. And the key concept of crop termination is that the fumigant must have both fungicidal and herbicidal properties as well. So we need the fumigant to not only kill or prevent the pathogen from producing microsclerotia, but we also need the herbicidal properties to decimate the plant as well. So crop termination has been investigated briefly, most recently in 2020 by the team at the University of Florida, looking for control of Macrophromina crown rot with the use of crop termination. But specifically for us, there are some knowledge gaps that we identified. First off, Verticillium wilt and strawberry management. We have not seen any studies that have been conducted implementing crop termination to control Verticillium wilt. But what we also do not see is any results looking at the adequacy of inoculum reduction, as well as the efficacy of different fumigant products. So I'll be discussing that a little bit more later on in my presentation. Another method for disease management is host resistance, and this is really becoming a main player in disease management moving forward. And it's the most effective and sustainable control method for disease control. We also see that for Verticillium wilt, we don't have any race-specific resistant R genes discovered yet. We do have some resistant genes discovered in Fusarium wilts, but more recently for Verticillium, there are investigations ongoing, but that identification of that resistant R gene is yet to be discovered. Furthermore, we see that screening for resistance to Verticillium wilt has high variation in germplasm resistance. And as well, we see that there's high frequency of moderately to highly susceptible cultivars found around the globe. What we have seen is that the most promising resistant traits that we could possibly locate is in these heirloom strawberry cultivars. But the problem with that is that it often brings along unwanted traits as well, like small fruit size or lack of taste, etc. So at the end of the day, what we see is that there is no completely resistant cultivar available for public use at this time. So the examination of host resistance is becoming really key, and the continuation of looking at different cultivars in different settings is also becoming important. The UC program in the state of California has been looking at strawberry genetic resistance to these diseases for quite some time, and there is publicly available information for our growers along the Central Coast. On the right side of the left side of our screen, we can see here that there's a different variety of publicly available cultivars. And then what we see here are these numbers and scores. And what the UC system does is they rate these cultivars from 1 to 4, with 1 being resistant and 4 being susceptible. So moving forward, when we look at the results from my evaluations, we'll be comparing our findings to the UC system as well. So for my research, I have a couple different objectives that I'm going to be discussing and evaluating. First off, we would like to develop new and enhanced soil-borne disease management practices within the California strawberry industry. But more specifically, we want to determine the effectiveness of the sequential applications of crop termination and bed fumigation on decreasing Verticillium survival. Also, we want to evaluate the efficacy of the integration of resistant cultivars with our chemical methods of pathogen level to reduce the further decreased Verticillium wilt of strawberries. And then lastly, I will to evaluate numerous genotypes and elite breeding lines for their resistance to Verticillium wilt. So now let's go ahead and turn to part 1 of my research, which would be evaluating that integration of those sequential fumigation techniques as well as host resistance. So for our experiment here at Cal Poly, we did this on the Cal Poly farm in field 25. And our experiment was a randomized split plot design where our whole beds were separated by the fumigant type And then what we did was we separated these beds into different subplots. And those subplots were receiving different fumigation methods. And those methods are as follows. Some of these plots could either receive crop termination and then also bed fumigation. Some plots could receive crop termination only and then no bed fumigation. And some of the plots could also receive no termination and only a bed fumigation. So in all, we had 12 industry standard beds that were 90 meters in length. And within these 12 beds, 9 of them were being treated and 3 of them were non-fumigated control beds. And within each of these 3 subplots that are located within these beds, we had roughly 310 plants, and they were aligned in 4 rows within 3 lines of grid. And this is an industry standard setup for the southern area growing districts, specifically the Santa Maria and Oxnard areas. So when we look at our field overall, we can see here that what we're looking at is a 3 replicate, and we can see here on the left side of our screen that our whole bed is separated by fumigant type. So you can see here the different fumigants. And then we also have 3 different subplots located within that bed, and then our control bed as well. So overall, this is what our experimental design looked like with the 12 beds in all. So specifically for the fumigation, we can look at what fumigants we used. For crop termination, we ended up terminating the crop 238 days after transplanting, when our crop was experiencing 5% mortality and 45% symptom expression. We utilized 2 different fumigant products for the termination. And these 2 fumigant products are labeled for use in a termination setting within the state of California. One is metam potassium and the other is metam sodium. And throughout the presentation, I'll be referring to their trade names, KPAM and VAPAM. Now for the bed fumigation, we ended up fumigating 112 days after the crop termination and 15 days before transplanting of the crop for the next season. We also utilized KPAM and VAPAM as well for the bed fumigation, but we also wanted to incorporate chloropicrin, which is by its trade name trichlor as well. So after the termination, we wanted to look at the injury produced by the fumigant. So this isn't the injury produced by the pathogen or the disease, rather it's the injury that's being delivered by the fumigant. And what I went ahead and did was I rated these crops on a scale of 0 to 4, with 0 being 0% mortality and no wilting, and 4 being 100% mortality with complete wilting. So we wanted to see if there was a correlation between the visual appearance of crop injury with whether or not the pathogen survived within the terminated crop. And when we think about the pathogen survival within the terminated crop, we wanted to look at the survival both in the petiole and in the crown. So what we see here on our screen is an example of a petiole infection with Verticillium microsclerotia growing out of both ends. And then what we see here is an example of a crown infection with the same microsclerotia growing out of the crown tissue. We also wanted to look at soil inoculum density. We wanted to look at how it was changing over time. So after the termination, we sampled the soil 10 days after the termination, and we can see Cooper is doing that above here. And then we also sampled soil after bed fumigation. We can see Joseph is doing that in the picture there. What we would do is we'd bring the soil back into the lab and we would pool the sample together. And we would then let the soil air dry on the lab bench for about 2 weeks. And you can actually see an example of that in the front of our room right now. After that, we utilized a mortar and pestle, and then we sieved the soil with a 200 micron sieve, where we then used an Anderson sampler to plate the soil. And we plated the soil on a semi-selective medium, NP10, and let those plates incubate at ambient temperatures in the dark for roughly 10 to 14 days. And after that incubation period, we would go in with a use of a dissecting microscope and count the number of CFUs that we found in order to gather and see what the inoculum density was. After this, what we also needed to do was change our field and turn it over. And so between the termination and the fumigation, our study really wanted to look at the adequacy of inoculum reduction. So we had to keep the soil where it was. So on the left picture, what we're seeing here is that after the termination, we removed the drip and we removed the plastic. And after that, we had to till the plant material into the soil by hand. After that, we then had to place drip tape by hand and then lay the plastic by hand. And I know some of you in this room were involved with those endeavors, and I really appreciate your help. And Thank you for that. After the beds were ready to go, we then transplanted our next crop. And what we see here is an example of our field day, or our Cal Poly Strawberry Center transplanting day. And I mentioned earlier that we wanted to use the integration of a resistant cultivar. So what we did was we ended up using a susceptible cultivar, Seascape, with a moderately resistant cultivar, Valiant. So we planted both of these two cultivars within our experimental plots to see how they behaved after the fumigation series. Once the crops were settled in for a couple of months, we identified a peak harvest period at the end of May and early June, where we then wanted to conduct a yield analysis. So what we ended up doing was we spent 3 weeks and we harvested twice a week during that 3-week period. And the way we did it was we harvested the fruit from these plots. We then brought it back and we sorted between marketable and unmarketable fruit. Marketable fruit is what we classified as marketable was fruit that was greater than 21 millimeters in diameter. It was free of blemish, free of disease, and that would be suitable and acceptable in store shelves. After that, we then weighed the fruit to see how our yield was differing, or how our yield ended up being after the fumigation series. So now let's go ahead and turn to the results. I mentioned earlier that we looked at crop injury due to the fumigant. And what we ended up doing was evaluating the crop injury both at 7 days after the termination and 14 days after the termination. And the reason we wanted to do that was we wanted to see if we were getting differences at those 2 different time points. Time is really important for growers. We wanted to see, was it worth it or not for the growers to wait an extra 7 days to see whether or not the crop had more injury, or if there's less likelihood of pathogen survival at that time point. So at 7 days after fumigation, what we see is that there was an overall injury percentage of 77%. Those 2 fumigants we used, K-PAM and VAPAM, did not have any significant difference in the ability to deliver injury to the crop. Now, at 14 days, we saw a different story. At 14 days, our overall injury percentage approached 90%, and we did see that K-PAM had a significantly higher injury rate delivered to the crop than VAPAM. Now, moving forward, what we can also look at is the pathogen survival. And what this figure is showing us is a log odds ratio. And the way we can interpret this figure is as follows. In terms of log odds, we can see what the likelihood of a particular outcome is after a certain exposure. So that likelihood of the verticillium survival after the exposure of termination. And so on the left side of our axis, on the y-axis, we see our 2 different fumigants versus the control. We see the petiole versus the crown, and then those 2 time points as well. So with the 2 fumigants, what we see is that the likelihood of verticillium survival in the terminated crop is almost 4 to 5 times less than our control plots. And that goes for both K-PAM and VAPAM as well. When we're looking at whether or not the pathogen was more likely to survive in the petiole of the strawberry plant versus the crown, what we see is that for both of the fumigants we used, K-PAM and VAPAM, the pathogen was almost 2 times more likely to survive in the petiole of the strawberry plant versus the crown. And also at those 2 different time points, we see that the pathogen was almost 2 times less likely to survive at 14 days compared to 7 days after termination. And whether or not the pathogen was more likely to survive in the petiole at 14 and 7 days, we see that it was also more likely to survive in the petiole at that 7-day mark compared to the 14-day mark. So moving forward, now I'm going to turn the page and talk about inoculum density. And what this figure is going to show us here is that on the x-axis, we have our different treatments. We have our control, which was our non-fumigated plots. We have our plots that were only terminated, our plots that were only bed fumigated, and then those plots that received both of the fumigation techniques. On the y-axis, what we're going to be looking at is the inoculum density of verticillium in terms of CFUs per gram of soil. And then you can notice here, we also have 3 different time points. T1 is denoting our pre-plant inoculum density. T2 is denoting the inoculum density after the termination. And T3 is denoting the inoculum density after the bed fumigation. So let's go ahead and start with our control plots. What we see is that a steady increase over time in terms of inoculum density. Our pre-plant inoculum density was roughly 7 CFUs per gram, And then at the end of our fumigation series, that approached 19 to 20 CFUs per gram. So we can see how much the inoculum can increase over that time period. Now, in terms of the plots that were only crop terminated, we see that our starting inoculum density was around 7 CFUs per gram as well. And after the termination, it did decrease to roughly 5 CFUs per gram of soil. But without the bed fumigation, we do see that the inoculum density increased up to almost where we started at 7 CFUs per gram of soil. Now, for those plots that were only bed fumigated, what we see is that we get an increase without a termination, approaching 12 to 13 CFUs per gram. But with the use of a bed fumigation, we do get a decrease in inoculum density to roughly 8 CFUs per gram of soil. Now, what about for those plots that received both fumigation methods? Well, what we see is that we got a decrease after the termination, but then we actually had a slight increase after the bed fumigation. So let's go ahead and look at these treatments individually and see what the results found. In terms of our plots that were only subject to crop termination, what we see is that we have our control, our plots that were terminated with KPAM, and our plots that were terminated with VAPAM. At the end of the day, what we saw is we had a significant decrease in inoculum density from our control and our treated beds. What we did not see is that there was any significant difference between our two fumigant products that we used. So although we had significant decreases with our two fumigants, what we do not see is any difference between the two fumigants themselves. Now, for the plots that what we also see is that we're not below that threshold for strawberry, that 2 CFU per gram threshold for strawberry. Now, for the plots that were only bed fumigated, what we're seeing here is we implemented trichlor as well, chloropicrin, VAPAM, and KPAM. And what we saw was that there was no significant decrease in our treated beds. But what we did see is that trichlor had a significantly lower inoculum than KPAM. But on the other hand, there was no significant difference between trichlor and VAPAM in decreasing soil inoculum. That is the same story for VAPAM and KPAM as well. So what we saw is that our lowest inoculum density resulted from bed fumigation with chloropicrin, trichlor, but what we also do not see is that we're still not below that 2 CFU per gram threshold for strawberry. So what about our plots that received both fumigation methods? Well, as you can see on the screen here, we have our control. We have our plots that were terminated with KPAM and then bed fumigated with trichlor. We have our plots that were terminated with KPAM and then fumigated with KPAM. And then we see our plots that were terminated with VAPAM and then bed fumigated with VAPAM. And at the end of the day, what we found was that the plots that received VAPAM and VAPAM sequentially had higher inoculum densities than those plots that were terminated with KPAM and then bed fumigated with trichlor. What we also do not see is that we're still not below that 2 CFU per gram threshold for strawberry, even with our sequential application of fumigation. So now we can go ahead and look at plant mortality. So after we did this, after the season was ending, we went ahead and looked at plant mortality as well. And on the screen, what we're seeing here is that our control plots, we have our crop termination only, our bed fumigation only, and then those sequentially fumigated plots as well. And what the y-axis is showing us is average plant mortality. We can see for our control plots, we almost had 70% of the crop having mortality due to Verticillium wilt. But on the other hand, what we see is that we did get significantly lower mortality in all of our treated plots versus our control. So we do see that the lowest plant mortality came from our sequentially crop terminated and bed fumigated plots of roughly 25%. But the good news is that we saw significantly lower plant mortality for all of our fumigation treatments versus our control plots. So what about yield? How much fruit did we get from all of our fumigated plots? Or excuse me, let's go ahead and look at plant mortality a little bit more closely. What we're seeing here on the x-axis is our fumigants we use, so chloropicrin and KPAM, VAPAM, chloropicrin. And then on the bottom, what we're seeing is our methods, crop term and bed fume only, crop term only, and control. And what we see here is that we had significantly lower plant mortality for all of our fumigation treatments compared to our control, but what we do see is that our lowest plant mortality came out of the terminated with KPAM and then bed fumigated with chloropicrin. And that makes sense for us because earlier we saw that the lowest inoculum density was out of the KPAM and chloropicrin plots. But on the other hand, what we don't see is any significant differences between these treatments here and then these treatments as well. So it seems as though that end of season bed fumigation may be the best route moving forward, but I'll discuss that later on. So now let's go ahead and look at yield. And what we're seeing here is that on the x-axis, we have our treatments, as I mentioned previously. But now we're also looking at our two cultivars we used, Seascape, which is a susceptible cultivar, and then Valiant, which is a moderately resistant cultivar. And what we see is that in our control plots, we had really low yield, actually significantly lower yield versus all of our treated plots. But what we do also see is that the Seascape and Valiant cultivars were performing rather similarly, in fact, statistically similarly in all of our treatments. And at the end of the day, what we see here is that the sequentially terminated and bed fumigated plots had the highest yield from these plots, but they weren't any different from the plots that received a bed fumigation only. So let's go ahead and wrap up part one of my thesis. What we see here for soil inoculum density is at the end of the day, we see that the sequential fumigation applications returned us back to our pre-plant level. So it prevented an increase over time due to the season. But what we also can see is that this is an implication for growers with heavily infested fields. That they're trying to prevent inoculum buildup over time, and they're trying to keep the field where it is as they control this pathogen pressure. We see that the sequential fumigation applications may be a good route to take. What we also have to look at is the efficacy of fumigant dispersion. So we have to look at differences in lines. I didn't mention it in this presentation, but it's important to think about the soil type we use as well. The soil type that we have on campus here is a clay loam. It's a heavy soil, it's a salinous clay. And most often what we see is that strawberry growers are more transplanting into more sandier. So in our study, we looked at fumigants in a clay loam, but moving forward, it may be smart to look at soil fumigation in more of a sandy soil. What we also see is that pathogen survival was 4 to 5 times less likely in a terminated crop. So what we see here is that could possibly slow momentum of the pathogen buildup over time. And another thing we have to think about is when exactly do we terminate the crop? I mentioned we did it when our crop was experiencing 5% mortality and 45% symptom expression, but is that too late or is that too early? And how accepting will growers be to terminate their crop before they get a good yield out of it? Also, is one application enough? Is just terminating once enough to control this pathogen and prevent the inoculum buildup over time? Or are growers going to have to do this after each season? We also have yet to do a cost analysis. So I get asked this by growers a lot. Well, what's the monetary, should I fumigate twice? Is it worth it? We're not sure. We haven't looked at that yet, but one thing we can say is that year 2 investigations are underway. So we are repeating this experiment currently. And after that's done, I think a cost analysis and a monetary analysis will also be able to be conducted to see whether or not these efforts are even worth it for our growers. So that was part 1. Let's go ahead and turn to part 2 of the presentation, which is evaluating host resistance in 74 different strawberry cultivars in elite breeding lines. We had 5 different breeding programs that we worked with, and we're extremely grateful and thank them for allowing us to evaluate their cultivars in our experiments. Driscoll's, Lassen Canyon, Planasa, Plant Sciences, and UC Davis all provided us with cultivars to evaluate. Planasa only did in the 2nd year of our study, but the other 4 did in both years of our study. And in our experimental plots, what we saw is that our inoculum density was roughly 8 to 10 CFUs per gram. So in the 1st year of our study, it was 8 CFUs per gram. And then in the 2nd year of our study, it was found to be 10 CFUs per gram of soil. So this experiment also took place in field 25 here at Cal Poly, and we can see here an overhead drone shot thanks to Dr. Bo Liu and the Bray department. And what we see here is that we had a randomized complete block design with 4 replicates outlined in red, and then also a fumigated control, which is outlined in yellow. And within those 4 replicates, we had 20 plants established per plot. So when we were evaluating our cultivars for disease progression and whether or not we were diagnosing them accordingly as verticillium being the causal agent of plant death, what we would do is that we would evaluate the crop every 2 weeks. So I'd go out to the field every 2 weeks and I would look at our plots and I would electronically record with both pictures and notes of what the plots looked like. And on this screen here, we can see some classic above ground symptoms of verticillium, but whether or not that is due to verticillium, we had to bring that back into the lab. So what we would do is we would bring the crop back into the lab and we would process the plants. And what we see here on the bottom of our screen is that noticeable black necrotic margin, but also the lack of crown discoloration. And this is one of the notable characteristics for verticillium in strawberry is sometimes in the early stages of disease infection, we see lack of crown discoloration. Now, we are still investigating that to see whether or not increase over time of disease progression could cause crown discoloration. But most often what our students saw in the pictures they took was the lack of crown discoloration. So what we would do is we would plate both the crown tissue and the petiole tissue on a semi-selective medium, NP10. And what we would do then is that we would let the plates incubate in the dark for around 14 days. And then after that, we would go in, and what we can see here on the top picture is an example of a plant that can positively be diagnosed as verticillium as the causal agent. And what we're seeing here are those black microsclerotia structures growing out from one side of the infected strawberry petiole. So let's now look at some results. As I mentioned, there were 2 years of this study. So what we're seeing here is the results from 2020 to 2021. We see a large variation in plant mortality from low plant mortality, average plant mortality as low as 8 to 10%, all the way up to close to 100%. And what we saw that overall within all of our 51 cultivars, we had an average plant mortality rate of 52.3%. And if we were to look at these mortalities by breeding program, we can see here that each of these breeding programs had wide variability in crops that were susceptible and crops that were resistant. So for the second year of our study, so what we can also look at is looking at our results compared to the UC system. So earlier I mentioned that the UC has publicly available information. And so I went ahead and popped up that resistance score here from 1 to 4. And then I went ahead and colored the UC cultivars that we also had. And what we're looking at here is that we have some differences actually. And if we were to look at our crops that we had in the UC classification and then the cow poly evaluation classification, we can see here that we could almost rate these cultivars a little different. So we can see here on the screen, we have 7 to 8 different cultivars. And then we can look at the UC classification and versus what we would classify the results as. And the way I did this was I looked at our 4 categories and separated them in terms of percentage. So resistant could be scored as 0 to 25% plant mortality. Moderate resistance could be scored as 25.1 up to 50. Moderate susceptibility, 50.1 to 75. And then susceptible as 75 up to 100%. So what we see here is that we do have some similarities, but we also have some differences between our findings in year 1 and the publicly available UC system findings as well. So now let's go ahead and look at the second year. You can probably notice here we had a very much lower mortality overall. In fact, we had a 35.8% plant mortality within our experimental plots this year. We can see that we had a mortality almost as low as 0%. And then we also had mortality almost as high as 85%. And if we were to separate these results by the breeding programs, we can also see, again, the wide range of susceptibility and resistance for all of these breeding programs. And if we were to do the same thing and look at these results compared to the UC system, we can also see that we also have more differences. We can see here that we have classifications of the UC system on the left, and then the cow poly evaluations on the right. So we can see here we do have some similarities, but we also have some differences. So this goes to show everyone that the importance of doing these evaluations over time in different locations with different cultivars is really important because one season isn't going to give us a good answer moving forward. So let's look at the common cultivars. We had 23 common cultivars from year 1 of our study and year 2. And we can see the first year of the study outlined in red and the second year of the study outlined in blue. You could probably notice there were a lot of differences. In fact, a lot of the cultivars in this graph had a lot of big differences, with the exception of BG63024, which performed relatively similarly in both years of the trial. So this just goes to show everyone that we do get different results year after year, and that's why it's important to repeat these evaluations each growing season. One thing we can also look at is weather. So weather plays a huge role in pathogen and disease development. And so what we're looking at on the screen is 2020 to 2021, year one. Red is outlining our daily maximum temperature, and blue is outlining our daily minimum temperature, with the black line denoting our number of plant mortalities over time. We can see here we started to get plant mortality due to verticillium in March of 2021. What we also notice is that over time, as we approach the end of March and early April, we start to see that increase in temperature. And with that increase in temperature, we also see the rise in plant mortality as well. So we can see here that verticillium is a rather cool weather loving patch. It likes those interdispersed warm and cool days, the coastal fog, and then the daytime sunshine. So for this trial period, we had roughly a 70.5 degree daily high temperature, which correlates to roughly 21.4 degrees Celsius. Now, for 2021 to 2022, we see some differences, not necessarily in the overall average daily temperature, which was 70.2, but what we can see is that there are a lot more oscillations. What we see here is there are a lot more differences. You can see up and down for both daily highs and daily lows. And what we're seeing is that our disease loss or our plant loss came this time around mid-April. And that did come around the same time as that our temperatures started to rise up over time as well. So weather plays a role in pathogen development. It's not the only factor, but I did want to share these weather results just to show you that although our weather was relatively similar during both years of the trial, there were some differences in terms of oscillations between temperatures as well as daytime and nighttime temperatures as well. So let's go ahead and get some conclusions for part two. What we see is that disease severity is affected by abiotic factors. We just saw that temperature plays a role. What we also see is that trial location and inoculum density are really important. We repeat these studies every year on the Cultivar farm, where we have a clay loam soil and a certain naturally infested inoculum density compared to an artificial inoculum, which could provide different results. We also saw that there was wide range of susceptibility among the genotypes we looked at, and ongoing resistance screening using new entries is needed each year. And I know that the Cultivar Strawberry Center will be continuing these evaluations moving forward. Now, at the end of the day, what we saw is that there was no completely resistant cultivar to verticillium. So let's go ahead and wrap things up overall and the impact of an integrative approach to disease management. What we saw is that the integration of crop termination, bed fumigation, and host resistance could help growers stop the momentum of pathogen buildup over time. It could help them increase their yield, but what it doesn't do is necessarily completely control in our fields. Complete eradication of this pathogen is not possible, but what we can do is try to completely control disease with the integration of different management methods. So moving forward from my research, what we can see is that the importance of looking at different chemical methods, but also looking at different genetic resistance methods are important moving forward. And I hope that research moving forward will also stress and focus on the integrative approach to disease management. So to wrap things up, I just wanted to share some pictures during my time over the past 2 years. I've been blessed with numerous amounts of opportunity, from field day up on the top to fumigation, different fumigation experiences. I was able to present my research at an APS conference in Pittsburgh and present at various conferences and research symposiums. I was able to work with a lot of different graduate students who have become my good friends. And I was also able to teach plant pathology labs, which is actually right here in this classroom here. And so I'm extremely grateful for the opportunities that I've had over these past 2 years. And I wanted to highlight some of the high points that I had. So with that, I'd like to give some acknowledgments. I'd like to first thank our funding at the Agricultural Research Institute and the California Strawberry Commission. I'd like to thank our product and fumigation services at TriCal and AMVAC, as well as our PCAs, Caleb Robertson, the Cal Poly alum, as well as Rob Papani. I'd like to give a huge thank you to the Strawberry Center staff, specifically Vivian Longacre for managing the lab and helping me so much within the laboratory. I'd also like to thank Drew Summerfield and Kyle Blauer for teaching me so much about field work. I couldn't have done it without you guys, and I've learned a lot about what it takes to grow strawberries. I can tell you it's not easy, but it's definitely worth it. I'd also like to thank master's students Yu Chen Wang, Mary Steele, and Anthony Bella, and also all of our undergraduate student assistants, both in the lab and in the field. So with that, I'd like to thank you all for listening, and I'll take any questions that you might have. Thank you.
So in part one, you find the results. You had two different cultivars in that study with the results on the susceptible cultivar or both combined, and then see it labeled on the graph.
Yeah, so the question for those on Zoom, the question was, we looked at both a susceptible and a resistant crop, and what was the results from them. What I highlighted in this presentation was our yield analysis from those two crops. What I didn't highlight was the mortality in terms of the two different cultivars. So in this presentation, what I highlighted was yield, and what we saw that there wasn't real significant differences between those two cultivars over time. But in terms of mortality, I don't have that information with me. Yeah.
Actually, the crop fermentation where the plants, or sorry, the bed fumigation, the plant's still getting water normally during that 14-day period where you're observing the mortality.
Yeah, that's a great question. The question was, were the plants still getting irrigation between that 7 and 14-day mark after the termination? And no, they weren't. So that could also play a role in terms of plant injury over time. We do expect the plants to die more when they get lack of water, and whether or not the injury correlated with pathogen survival, what we saw is that it did. It was less likely for the pathogen to survive in the crop at that 14-day mark. So the lack of irrigation could play a role as well, but the effect of the terminated products on the herbicidal properties and the fungicidal properties seem to be rather effective. Yeah. If anyone on Zoom has any questions, you can put them in the chat, and then Dr. Hewavitharana will moderate those for me. Yeah.
So we talked about this, there's a bit of a tension between getting profitability out of the crop and terminating it for disease kind of purposes. And talk a little bit about what that decision might be like for the grower. What are the trade-offs with terminating the properly versus waiting a lot longer?
Yeah. Yeah. So the question was regarding termination and how growers would, tend to time the termination, whether or not in terms of monetary reasons why they should terminate at a certain time, or whether they don't terminate.
Well, the monetary part, what's going through their head?
What's going through their head, obviously, they want as much yield as they can get out of their crop. So for them to be open to terminating their crop and stopping that yield at a certain point may be a reason why they don't want to terminate. But on the other side of things, if your pathogen pressure is so high that you're not going to get yield, as much yield as you would think you're going to get, then a termination may be worth it, because moving forward for your next season, it could help slow the momentum and possibly give you higher yields moving forward. So growers really have to think about, do I take a loss this season in order to help myself next season? And is that even worth it to terminate my crop with the cost of fumigation, cost of the plumbing, PCAs, et cetera?
And do you think your data is compelling enough to step to which one of those two? To
Yeah.
wait or to go early? You chose it kind of, I don't know how arbitrary the 50% line was. How did you come up with 50%? What do you think? How compelling do you think the data is?
Yeah.
To really that one?
Yeah. So why did we terminate when we did, and how compelling is the data? to prove that. Well, before we wanted to look at trying to figure out the specific timing of the termination, because in the literature, what we saw was there was no recommendation for a certain timing. So what we found and what we saw was that we thought that once half of our crop was experiencing symptom expression, it would be worth it to terminate the crop. Because once the crop was showing symptom expression, the berries would often desiccate and they wouldn't be harvestable and wouldn't be able to be harvested as well. And so again, this is the first study that's really looking at crop termination in that regard. And moving forward for second year of the study, we did terminate at a rather different time. And so we'll look at those results moving forward as well to see if we got better results in terms of inoculum reduction as well as pathogen survival. Yeah. And in terms of my results and whether or not they're compelling for growers or not, I always preface it with this is just 1 year's worth of data, right? And so we want to see what year 2 gives us. But from my findings, what we saw in terms of soil inoculum, plant mortality, and yield, and end of season bed fumigation gave us rather similar results to those sequential termination and bed fumigation plots. So growers might have to also take that into mind. Well, is termination even worth it if bed fumigation is giving me rather statistically similar results in terms of yield and plant mortality as well?
I wonder, as far as marketing, too, what the conditions of the market are determined when they want to terminate the crop. Last year's strawberry harvest was very popular with growers in Shashika, not so much this year. So, looking at the long term, might be the top or at least the soil, like keeping the crop on the ground a little longer, you might want to maybe leverage some marketing.
Yeah, that's a great point. And market changes every year. What we saw in Salinas this year was that a lot of people decided to grow strawberries, and so there was almost a surplus, and they were getting less amounts of on a per acre basis. And so that it does change every year. And I think that growers really have to think about whether or not terminating the crop is worth it if they aren't seeing the necessarily market prices they want. So if you're not getting the market prices that you might want, it may be worth it to terminate just to try to control your disease pressure. And another thing to note is that growers often lease their land out, right? And so you have to talk about those who own the land, what the crop rotation strategy is going to be moving forward. They don't usually go strawberry, they'll rotate through different amounts of crops and everything. So would the termination also benefit other crops like lettuce, like broccoli, like cauliflower? So that is something that growers need to think about as well, for sure.
I know you guys looked at the different temperatures throughout the day, the moon and back. You guys also look at the temperature of the soil in the bed.
So the question was, do we also look at the temperature of the soil in the bed? No, we did not. We just looked at daytime temperatures and see if that gave us some similarities between disease incidents. And what we saw was that it might have played a role, but in terms of soil temperature, we did not analyze that, no. But I think that may be important moving forward. Verticillium tends to colonize plants in soil temperatures between 68 to 75 degrees Fahrenheit. And so that might also play a role in whether or not we had more overcast days this year than last year. Could that change the temperature in the soil? What type of tarp were we using? Was it black? Was it a skunk? Was it a striped? That all plays a role as well in disease development.
Uh, 2021 versus 2022, the percent mortality is really good. 52% in 21, and then about 36% in 22. What do you think explains that? What are the variables that?
Yeah, so the question was, how could I explain such drastic differences between year 1 and year 2 of our study in terms of plant mortality?
You did have both parts of the common in both years, 23 years. So really, you would only be fair to compare the average of those 23, because you have different, otherwise you have different entries, right? And that might explain some of it. Sure. But also in that chart, it looked like everything in 2022 was the bars were lower.
Yeah.
If I'm not mistaken. So I'm interested in what that number is, the average for both of them.
I don't have that number off the top of my head. It is in my thesis though. So I could reference you to that. But in terms of the differences between the years, we saw that in year 2, 45% of the genetics in our field were different. But in terms of the 23 cultivars, we saw there were a lot of differences as well. We see that weather could play a role. but we saw that weather was relatively similar in terms of daytime highs, 70.2 and 70.5. What we also saw in year 2 is you had a higher inoculum density, right? We went up to 10 CFUs per gram versus 8 CFUs per gram. So I think that, when we're looking at these results and trying to figure out why, what we did not see during year 2 was a drastic heat wave. And when those heat waves come, what we see is that we see progression of disease symptoms. So we don't see verticillium often colonizing plants at a larger rate at those high current temperatures, but what we see is the increase in disease symptoms. Because as the temperatures get hotter, the plants need more water, and with the lack of translocation of water through the plant tissue due to the colonization of verticillium, it causes more symptoms to develop, right? So in year 2, we didn't get that drastic heat wave, which may have led to the less progression of disease symptoms, which may be a reason for that. We saw in terms of the trial periods, they were relatively similar. So I don't think that could have played a role in the differences. But from the literature I've read, and if we were to think specifically about the cultivar Monterey, which is something that's widely used along the California Pacific Coast, you also saw differences between Monterey and 2 different years of the study as well. And I also saw that as well too. So it's really interesting to think about, quantitative trait loci, what genetics are playing a role in preventing disease development. What cultivars have certain traits that could lead to disease development at slower rates. So I think it's something moving forward in the literature that I've been reading over the past 2 years is trying to figure out the relationship between inoculum density between all these different cultivars and how disease development occurs. But in terms of the 23, we only saw one of them performing rather similarly, and the other 22 were extremely different. So I'd like to compare those results to the previous years of the study as well, and also the future results. But in terms of that, I think it's still to be investigated.
On the cultivar, common cultivar ratings, that who made those evaluations and why there may be is there any data support their ratings?
Yeah, that was one thing we could not figure out was how the UC system rated their resistance scores on 1 to 4. Oh, sure. The question was, how does the UC system rate on 1 to 4, and how could we correlate our results and our scores versus theirs? That's a good question. We could reach out to Glenn Cole at the UC system, et cetera, to see how they do it. Do they classify their resistance as completely resistant, or do they give it a more arbitrary 0 to 25? So that's what I did for our studies. I just separated them into 4 different quadrants and then looked at our results compared to theirs in terms of average plant mortality. So that is how I wanted to compare to the UC system's results. We do see similarities, but we also do see some differences as well. So again, year after year, we see all these differences. And so we have to figure out moving forward with more investigations, how exactly our results match up to theirs. And I know that our data often supports their ratings as well, and how they rate their publicly available cultivars too.
I think the interesting ones are we have it as the one that they have it for.
Yeah.
We have 1 to 2 and they have 1 to 3.
Yeah.
That's pretty close to
Oh, sure. Yeah, the complete opposite ends are interesting. And from Yu Chen Wang's studies with macrophamina, she also saw some differences between the UC system and our results as well. So that just goes to show how year after year, whether that's different irrigation patterns, whether that's different weather patterns, inoculum density, type of inoculation, was it natural, was it artificial, that all plays a role as well in figuring out these disease ratings. And so at the end of the day, our results really help the UC system in seeing how we can really give a good rating to this publicly available information for the growers as well. Mm-hmm.